Happy Monday. Let's move my microphone out. All right, audio is looking good. Stream preview is looking good. I think we're set to go. So this week we'll be continuing my journey into learning deep learning. Looking through what we got last week, we had created an extremely simple neural network. And then we moved through the journey that I had done in chapter 2 and 3 in the book, which was going through the different inputs and outputs. So single input of data, single output of prediction, multiple input of data, single output, input, multiple output, and then multiple input, multiple output, which is where we finally landed here. And this has the matrix math, the one that has the scary mathematical names. But we're not going to worry about those right now because we're going to move on. Now, I thought there was going to be more to chapter 3, but it turns out that it was just explaining what was going on. And chapter 4, which I got through this weekend, is really interesting because it's where we start getting into actually the learning part. Because so far, this is just deep because there's no learning. But now we're going to change that. So I'm going to create a new file here. I'm going to call it actually learning, simple neural network.js. And I don't really mind like recreating a bunch of these things, repeating like repetitive sort of building and burning these down. This is actually how I learn the best, just doing this. So if I open up and we go to chapter 4, right, it starts talking about the different process of learning. And it only introduces 2 different types of learning. So the first one is called hot and cold. And I guess what we could do is we could create our basic, super basic single input, single output neural network, and then go from there. So we'll have our function neural network, which gets an input and a weight. And this simply returns input times weight. And I guess like to do a prediction with this, we just call it, and then there we go. We have a prediction. So if we have, the book kind of started breaking down and not using even fake data. It just started talking about like, hey, what if we like, we have some random data. So for example, if I have input of 0.5 and a weight of like 0.3, 0.3, then I can get, oh man, I'm programming like Python again. Const. Okay, then I can get my prediction and set that equal to the neural network. And once I have this prediction, I mean, previously we were just printing out what we have, which I guess we could do that here. We can console.log prediction, and we'll see what we have. So 0, 1, 5. Now, what can get interesting is if we have like a goal where we actually like what is the correct prediction that we want. And this is, I believe, part of supervised learning for neural networks. So we're going to give it known input like from older data, and we're going to have a known result. So that's going to be something we want to get up to, I don't know, 1 maybe. So in that case, we're way off with this initial prediction. Now, of course, our weights are what's way off, but I mean, it's not really that interesting if we manually change our weights. We want to do this dynamically because we don't know what our weights should be. So what we can do is we can get the difference. We can get the difference between what we guessed, so the prediction, and what we're supposed to guess. So this is called the prediction delta. All right, so this is going to be the prediction minus the known result. So we know that's going to be what? 0.85. So we want the amount that it was erred by. So const the error, the prediction error, is, and this is a little bit interesting. It took me a little bit to like fully understand why we're doing this. We're going to take this prediction delta and we're going to multiply it by itself. And I think that just setting it to the power of 2 is all we need to do. I can't remember if there's a math thought like POW. JavaScript math power. There is a math.pow. It's like 7.3. So 7 to the third. Is that 7 times 7 times 7? I think. Yeah, base and exponent. So what I would want to do is do math.pow. Prediction delta is our base, and we want to raise it to the essentially just multiplying by itself, but to the second. And this does a few different things. If, for example, this is negative, this will make it positive. This will also make really big errors, really big, or so really big wrong predictions. So prediction deltas, huge errors. But it will scale up. I don't know what the curve is, but like a huge amount. So it will just go straight. It'll be a line like this, exponentially. I guess that is exactly what we're doing. So if it's a small error, it will stay near where the actual prediction delta was, and that allows us to change quickly. So if our known result is actually supposed to be like 1,000, we don't need that many more steps. Okay, so that gives us we have our prediction delta, we have our error. We also want our change amount. So if I do something like 0.01, this would be like how much are we going to change our weight by? And this the book actually has us do this once. And it's usually a terrible idea to like have a fixed change amount, because you want to get smaller as you get closer to it, so you can at least try to get exactly the known result. Although I do notice that like the cut in half problem comes in where you're just going to get really close to it, but never actually get there. That being said, you can get like extremely close. This, however, has a chance of just overshooting it completely, because if we're not just 2 decimal points away, if we're like 0.1 decimal point, we're just going to start flopping over it. But I'll keep this for right now, and then I'll show like the way to solve that problem. So we have our prediction delta, we have our error. I think then we get our the weighted error. Although I guess we'll start with the change amount first. So like this is a very naive approach. And so we need to know, did we which side, up or down, did we predict on? And I think that the problem is that when I did this, get this power of, I lost the direction of the error. So my thought, although I have this, which helps, if my error is like below, then I want to like increase up. And we only do this once, so in the exercises, so I need to remind myself what this is. Where is the... Oh, okay, so we do the power of, we get that, and then... So the book talks about it as if we miss by like 2 inches. So let's say we're talking about like we've used sports here. So if we're using like a sharpshooting competition, and you fire and you hit the bullseye, but you miss by 2 inches, did you miss up or down? We've now got a positive number no matter what, which means that as far as we can tell, we missed up, but we might have missed down too, and this wouldn't tell us. So what we can do is we can get this number and try again 2 different times, once with adjusting the weight up and once with adjusting the weight down by this change amount to see if we get closer to the known result. And if we do, then that means that that's the way to go. So this is called like the hot and cold method, and it's I think it's never used. It's just a training, sort of like to see how one way it can be done. It's also incredibly inefficient, as we're about to see. So if we want to go one step, let's console log our prediction and our prediction delta and our error. So prediction is 0.15, our delta is negative 0.85, so we missed on the bottom, and our error is now 0.722. And this is after taking the power of, so this is this is negative 0.85 to the power of 2. So I want to do this entire thing again, but change with a change amount up and then another time with a change amount down. So const prediction up equals, we're going to pass our neural network. It's going to be the same inputs, but the weight is now going to be plus the change amount, which means we can now get the prediction up delta equals the prediction up minus the known result. and then const error up equals so that gives us we can sort of like guess what happened when we went up, and then we'll do the exact same thing and head down. All right, so we now have our error up. So we have an error when we just do it like the normal ways. We have error up when we tried to go up, and we have error down when we try to go down. And I guess we could console log all these. We have prediction up. We have prediction up delta. And we have error up. And so here we got our original, here's the up, and here's the down. So I guess if we take a look, and the way it has it is if our error, so this is the first error, if this is greater than error down or error up, so our error is here, it is greater than this error, it is not greater than this error. Which means we want the error to go down to 0, or at least as close to 0 as possible. So that means that this is the one. So that would be our prediction up. We should be moving up. And that kind of makes sense, right? Our prediction was down below, so we should aim upwards to make this number go up. Although, right, to go up towards 0, which it's a negative, so like going up is the opposite direction we want to go, because that's going further down. It's a little bit of weird because we have to think in negative numbers. But the way we can write this is we can say, all right, so if our error is greater than either of these other errors, then we're going to go ahead and do the rest of it. So if it's greater than error up, or if error is greater than error down, and I'm going to go ahead and make this like a nested if statement here, because I think this is going to be a little bit easier to read. This is also the way they do it in a book. So I want to now figure out which one I want to go. So we know we want to go up. And the reason we know we want to go up is because this error is smaller. So we can just check to see if error, I guess we know where we're supposed to be going, so we're now just going to see if error up is less than error down. Then we know we want to change the weight. So the weight is going to be equal to weight. So error up is less than error down. We want to go up. So plus change amount. Yeah, I think I got that correct. And I don't know if I want to do an else here. Probably. So an otherwise, we're gonna have, all right, now that we're doing an else, I wanna just make this like that. If error up, we're gonna do wait equals wait plus change amount. Else, our wait is gonna equal wait minus change amount. And then we can, we'll try again. And we do this until we reach the known result. So what I can do is put this into a loop. So starting right here, so the book constantly does for loops. That way it doesn't last forever. And also because we rarely will get to the exact answer. Only if we like set it up for ourselves really, really nicely mathematically. Otherwise, we're going to get to something like this with this many decimal points. And so we'd have to do math to make sure like we're within this range of it. So for right now, we can just do some for loops. So for let count. And this is really for just looping through n number of times. So we're not even going to use this. We can just do that even. Equals 0. Underscore is less than, let's say like, we can even do 5 times. And then underscore equals underscore plus 1. I'm using underscore here because that can denote that I don't really care about this variable and I'm never going to use it again. Obviously, this won't work if I have Lodash installed. All right, so we're going to move this up in here. So now we're going to constantly predict with the neural network, calculate our delta, calculate our error, then do the prediction going up and doing the prediction going down, detect which one we want to do, and then change the weights, and then try the entire thing all again. In the meantime, we're going to I should probably only show our prediction so we can see which direction we're going and if we're getting closer. And we're doing this 5 times. Assignment to constant variable. Uh-oh, this needs to be a let. All right, so our guess is 0.1. Our prediction is 0.15, and then 0.155, 0.16. So we can see it's actually getting closer to 1. It's just taking a really long time to get there. If I change this change amount to 0.1, you can see we're getting there quicker. So if I go through this loop enough times, we will get to 1. Which is exactly what we're trying to get our network to do. So this is a way of learning, and I could then set up a while loop for this. So let's try that now. So while true. And at the end here, after our console log, if the delta, so if the prediction delta says the prediction minus the known result, if that is less than like 0.00001. So this is the prediction delta, and we see it's coming down. It's also negative, so I kind of want to make this a positive number, which I know there's a math for that. Absolute value. So yeah, I could do that. Math dot absolute value of the prediction delta. If that is less than, and I want this many zeros, so I'll take U. I don't actually know if this is, no, that's not right. I don't know if I can actually get this close. I think with this one, we're going to get to the exact value, so it won't matter. You need to be in parentheses. All right, I think we're going to get, oh, right. If math, this, we go through that, and then we want to break. So we should see this just like spit out these predictions over and over and over again until it gets to 1. Never-ending loop. So let's see what happens. So our prediction is 1 with a whole bunch of decimal points and then a 2 at the end, which means our prediction delta is this. So we never really got to this here. I wonder if I should like go down to that instead. There we go. So this is how close we got. And we can see the progression here as we get closer and closer and closer until eventually we get so close and it's that cut in half problem where like we're just sort of staying here. And we're probably flipping back and forth because this was this was over the guess. And regardless, I could change the known result of where we want to go to. And this algorithm will learn its way to it. It'll learn in an incredibly slow way though. So there is a better way here. So if change amount, instead of that, what we can do is dynamically choose our change amount based on the input to sort of scale. So we can take our the prediction delta here and make this what's known as a weighted prediction delta. So const weighted prediction delta. And this will be a prediction delta times input and then we can use this so to go up and down. So prediction up is going to be weight and I think, well, this is where it gets interesting because now we don't have to guess like this. Because prediction delta can be different. I should not. I'm getting ahead of myself. There is that way, but it's not. We can't do it with the hot cold method. I think this is the only way to do hot cold method, as far as I can tell. Or at least they don't really talk about that too much. But this is possible. Like this is a full machine learning, or not machine learning, deep learning algorithm here. It will get to 1 by setting the weights. And I could do this entire thing with a multiple input and multiple output, and it will still work because I just do this algorithm for each of the inputs and weights. That being said, that's a lot of, that would be a lot of these extra predictions that we have to run just to find out, just do a little bit of calculation. So it's way too inefficient. All right, so moving on. So then the book talks about needing to learn the, what is it called? The derivative. And the derivative, I think, is this thing. So if I were to name this derivative, so const prediction derivative, I think that's horribly misspelled. Derivative. I believe that would be equal to the prediction delta multiplied by the input. Katali, hello. Welcome to the stream, or good morning again. Yeah, so my wife is much more of a math person. I think she actually graduated with a major in math. So I was talking to her about it, and she has more of like a classical definition of derivative. And I'm still struggling with like the not in this specific context definition of derivative. And the other problem is like the symbols that are used to use, like in Khan Academy, for example, was not really helping me understand it. But from what I can tell, it's and for the way this book describes it. Did you say she thinks she graduated with math? She graduated with a math major degree. I guess like I sort of trailed off and didn't finish my sentence. Also, hello, good morning, stacking. So this derivative is the speed at which we're changing the weight. So we have our known result, we have our input, and we have our prediction. And we want to say, okay, given that we have a larger prediction delta, we need to move faster to get to this known result. And it would be the opposite. We want to move slower. And so this input this derivative multiplying the prediction delta. So if we remember, it was, I think, 0.15. So we multiply that by input, and we get, I don't actually know what that is off the top of my head. But clearly it's going to be a scaled number, essentially, that then we're going to be able to use to say, okay, we're going to change the weight by this derivative to move towards the known result. As we get closer, our this guess will get smaller and smaller and smaller. And that apparently is the key for the next this next algorithm we're going to go through. All right, let's see. Let's see, what am I missing here? Oh, yeah, okay. I like how they have a section called just give me the code, and then they just, print out all the code here. And then they have like the rest of the chapters just describing that code that we wrote. All right, so if we go through in this direction, like this way now, we have our neural network. This is going to be the same. We have our input. We have our weight. We have our known result. This is where we're trying to get to. We do our infinite loop. We get our prediction. This is all the same. We get our prediction delta. We get our error. So like none of this has changed yet. But then we get our derivative. And we don't need to do this anymore. We don't need to like predict up and down. So now we're going to say we want to, we don't need this anymore. I'm going to take that and I'm just going to call a break at the end here, just so we run once through. Let's console log our prediction delta, our error, and now our prediction derivative. And so our derivative is this negative 0.425. And so we need to move our weight by the opposite of this in order to change. So we missed low, so we need to move up. So what we should really do is change our weight down. So let me add weight in here. And then we're going to say, okay, weight, we want to equal weight minus the prediction derivative. And then I want to, nope, that's not the command to duplicate. I'll do it the hard way. So we say, okay, we got this, and now our weight starts at 0.3, and now it's 0.725. So we moved it up, which hopefully will bring us closer to our known result. So we don't need that like change amount anymore. We do need something else, but we'll get to that in a second. All right, so let's try running this. We'll bring back our if statement. And I think this should work. Let's find out. Oh, no break right there. And we can see we went through a whole bunch of these iterations, but our prediction is still going closer to our goal. And then we eventually got to within this amount, which is whatever percentage we're willing to have as our potentially incorrect. But we got there. And our weight at the very end, yeah, that's this weight here, was 1.999999. And that's not too bad. We're able to get there. Now, if we have an input, I think if I start with maybe even just 2 might cause this to break. Yeah, we got into not a number territory pretty quickly. Let me see. Oh, it even lost. It was too fast. It lost the previous output. I think we ended up going into too big of numbers, and that's because our prediction derivative, which is telling the weight by how much to change, started missing wildly, and then it kept on growing bigger and bigger and bigger as we have like, okay, here's where we want to be. Here's our known result. It's like, oh, I'm right here. Let me try this. And it comes to the other side. It's like, oh man, okay, that's too bad. Let's try it again. And it comes farther out. And then it just keeps on wildly swinging. So there is a way to solve that, which is to put a cap on how much the derivative is allowed to change the weight. So they call this the alpha. So I'm betting that that's the actual computer science term for this. This is essentially, so I could call it the alpha, equals, let's say 0.01. Apparently there's not really a science for choosing this. And we're going to call this the weight change limiter. And so now when I change the weight, I'm going to multiply this by the alpha to scale down whatever change. Make it really small. Let's try this again. And we're back in business again. It takes a whole bunch of steps to get there, but that was the only change we needed to do to get to within 1, 2, 3, 4, 5, 6 decimal places of our guess. And this apparently is like the standard way of doing deep learning neural networks. It's just a single input and a single output, but for the most part, this is exactly what we would do for all the different types of like multiple input, multiple output, and so on. So moving through that. Let's see. I really like that in the chapter it had a section where it's like, okay, now like spend some time and try to write this from scratch. Like, don't bother like reading the code. Just actually try to memorize, and even if you can't memorize, like recreate this entire thing, which I think I've been able to do. I've been programming it using the coding language the books recommends, which is Python, which is why I constantly forget the const now. But I do, so far I am enjoying this book. So then it moves on and says, okay, well, from now on, we're just going to use this sort of general style. And now we're just going to play with multiple inputs, multiple outputs. So if I want to go with multiple inputs, what needs to change here? Well, this is going to be an array, and this is going to be an array of weights. So if we take a look at that, our input, if we have something like 0.5, 0.2, 0.9, our weights is going to be, each input is going to have its own weight too. And I think that's the key. So we can say like, the weight is also like the volume meter on this. So I can say, okay, this first one, this doesn't really matter that much. So it's a 0.1. This second one matters a whole lot. So this is a 0.9. And this is completely guessing, but the network will correct for our guess later. And this one's just sort of average. I'm just going to do 0.5. Our known results. This is what we're going after. We'll keep this as 1. Our alpha can say the same too. Then we get a prediction. So we have our neural network, we throw in the input, and we bring in our weights. And now we have to like actually do something with it. Well, it's another function. So obviously, clearly doing this won't really work. This is that weighted sum, which is also known as a dot product. The dot product is the computer sciencey term. The weighted sum is slightly less computer sciencey. And vector multiplication plus an array sum is really what's going on here. So I'll do these as separate functions here. So we have a vector multiplication. This is going to take a vector 1 and a vector 2. And we're going to multiply these two against each other. Oops, sorry, I hit the microphone. And then return that array, like a new array. So I need them to be exactly the same length. So I'm going to throw. So if vector1 dot length is not exactly equal to vector2 dot length, Mimiron, welcome to the stream. Good morning. Pagchomp? I don't think I know what that reference is. Okay, so if they're not the same length, we're exiting out. We want to create a new array so I can do the map that we did before. So I'm just going to say return vector1.map. We're going to get the value. So whatever this number is, we don't really know what it is. We just know the numbers. And we're going to get the index. And we want to return this number multiplied by the vector of this one. So it's going to be the number times vector 2 of index. Oh, yeah, I guess I don't have that emote. PagChomp is a better version of PogChamp. Well, I don't know how to get those emotes. I guess I could create my own. I think I can create one. I don't know what I would want to create. Okay, so this should get that. We can test this really quickly. I'll console log out our while loop here. Console.log vector multiplication. We're going to take in 1, 2, 3, 4, 5, 6. So we tried this last time. 1 will be 4, 10, 18. So we should get a single array of 4, 10, 18. Which is what we got. So this array works, or this function works the way we want it to work. The other thing we need to do for the dot product is to sum it. So I'm going to say function vector sum takes a single vector in, and we're going to return vector dot reduce. So we're going to get our sum, and we're going to get the next number. And we need to return the sum plus the next number, and we're going to start with 0. Okay, so if I do this, this will be 1, 3, 6. So we got 6, so perfect. And then the dot product is the actual combination of these two, and that's the computer sciencey term. So I'll just use that so it's in here. And we're going to take two arrays. So this is a vector 1 and a vector 2. They have to be exactly the same, but we have a throw error here, so I don't really need to test it in this one. So we're going to return. Can I do? Oh, I can just do the dot product. Dots. Wouldn't it be a better name for the function to be vector multiply? Oh, you're probably right. Vector multiply instead of vector multiplication. All right, that looked like I had accidentally selected the entire word. All right, so we now need to combine both of these. We're going to multiply first, and then we're going to sum up the result. So return vector multiply, pass in vector 1 and vector 2. We're going to take the result of this vector multiply and we're going to pass it into vector sum. I don't think I can, right. I'm going to put that over here. Vector sum. All right, so vector sum, the result of vector multiply of these two, and return that all the way in. So we'll start with our 1, 2, and 3, 4, 5, and 6. So we know this is going to give us a 4, 10, and 18. So 4 plus 10 is 14, plus 18 is 20, 32, I believe. Yeah, thanks, Kotali. 32. All right. So here's the functions that we need, that I believe we need for this. We might, if I need another one, I'll just write it then. So this neural network is now going to do a dot product on the input and the weight. And that's going to give us our single output that allows all of this to happen. So we're going to get our single prediction from this neural network. And then we can get the rest of this prediction, delta, which is the prediction minus the known result. And then we have our error, which is just taking that to the power of 2. Here's a problem. Our prediction derivative needs to be multiplied by the input, but the input is an array. So we need to multiply it by each one of these to get a unique derivative per input. And that's how we know how much to change each of the weights. So this is another function we need to add in here. So, all right, function. this is going to be a single number. That would be this prediction delta multiplied by a vector. And we did this when I was making games before, and so they keep on, what do they call it? They call this the unfortunate name of ELEMUL. I don't know if they really go like expand that out. I think it's like elemental multiplication. I'm not sure, but what it reminds me of is this is actually scalar multiply. So a scalar number with scalar vector multiply. That's what it really is. We're taking a scalar and multiplying it by a vector. And we're returning a vector, a new vector. So we're going to loop through our vector, multiply it by the scalar. Actually, you know what? I was thinking of Python. I can map through this. So return. So this is going to be our number. It's our number times scalar. And so if I want to test this, I'll call scalar multiple, and we'll pass it in, let's say 2 and 1, 2, 3. So this should be a new array of 3, 2, 4, 6. And that's what we got. So in here, where we have this prediction derivative and we're getting the prediction delta and multiplying it by the input, this is now going to be calling the scalar vector multiply and passing in the prediction delta, that's our scalar, and the input, which is an array, a vector. And we get this prediction derivative back. And our weight has to be different now too. We need to update each weight specifically by its amount, which is a little bit interesting because each of these items in here are just number values. So I can't get them by reference. So I can't just like for each through it. Not quite as easily. I need to update these like very specifically. Now I can just say something like this. I can just replace this entire array with what we have here. So weight is actually going to be weight dot, we're going to map through this to change it. We're going to get a current weight, and we need to take that and subtract it. So current weight minus the prediction delta, prediction derivative multiplied by the alpha. And that should give us our new weight array. And then we should move forward. So I think this will work unless I screwed something up horribly. Oh, weights. Weights equals this. Where else is that used? Weights. Oh, that's lovely. Not a number. Okay, so I didn't do that, right? Let's see. I do see that it is an array of these. I just screwed up some of the math somewhere. So we know that the functions are working. We're just using the functions incorrectly here. So the input is this array. What I can do is just try it once again. And we'll break right after this. Actually, I want to break. Let's see, map, current weight, get the current weight and subtract. You need to be in parentheses. As long as the order of operations is followed properly, this should work. Otherwise, I'm going to need to go tell whatever, like prettier, that it's stupid, and to stop changing my math. But if it really is following a proper order of operations, then this will work. So let's just break here. And we can console log the new weights. So this first one through, obviously it's okay. We knew that it was going to be fine to begin with. This next one, the weights are not quite so happy. So this didn't really work out too well. So what did we have here? Our prediction delta is this second one. So right there. Our input is this. Let's actually try putting that in here. So we're getting this number, like it's an actual thing here. Scalar, okay, so we're getting this prediction derivative properly. Oh, yeah, that's silly. This is an array. I can't just do this. It needs to be based upon whatever the current thing is. So the current weight, we then need the index to grab it from here. That's what we need. I should also add this on. Unfortunately, it doesn't start, well, unfortunately, I don't want it to start automatically every time, but when my stream starts, it'd be nice to turn on. That way I could have you guys help out. All right, let's try this again. There we go. That's what we wanted to see. So if I take out this here, it's a little bit hard to read because it's like too many things in one line anymore, but we got to our prediction. So the book then goes through and talks about like why this works. And as far as I can tell, what's going on here is that we have three inputs. We have a single output that we're going for, a single prediction. And so we say like we're off by X amount. That's our prediction delta. And then, of course, we blow that up. We blow it out of proportion. And then we say, okay, each of you weights, we're off. We all missed. So change by the amount that we believe you are off. And that's what's happening here. We're calculating how much to change each of the inputs. And there's no intelligence here to say, well, we actually believe that this input was correct. Like we really need to increase the weight for it. It's more of like everyone was wrong, so everyone changes by the same amount. I can actually, and the book talks about doing some other cool experiments with this. We could freeze this and say that this weight will never change. It's always going to be 0.9. And yet we'll still get to the correct answer, but it's not necessarily good that happens. It's more of, hey, everybody else is trying to get to the correct answer. So since you're refusing to move, everyone else moves more to compensate. But that doesn't mean we get accurate results. And that's kind of how this machine learning thing works. That's multiple inputs. And what I haven't done is, I think the next thing I need to do is this algorithm is called gradient descent, by the way. And it's called gradient descent because when if we were to graph it, we're on some kind of gradient and we need to descend towards, so we have the amount of error on the left and the weights on the bottom. So we want to change the weights to then move our error down to 0. And so that's where we're going down. All right, so what I haven't actually gotten into the multiple outputs yet. I can guess how I think it's going to work, and that's kind of what I've been doing with the book. I actually wrote this one before reading how it's supposed to do it. Multiple outputs should be very similar. We're just taking a single input. So that would be 0.5. But then we also have these multiple outputs, multiple weights still. We're still going to, a known result is now going to be an array. So we're going to go to 1, maybe 1.2 and 0.2. Is where we're hoping to end up. Our alpha will remain the same. We have to create 3 predictions now. And so I think that's really going to be the same as when we had a 1-to-1. So instead of a dot, which just creates one thing, I think it's just going to be a pure vector multiply. Which is the input and the weight multiplied against each other, which is how we did that 1-to-1. So we'll just do vector multiply here. That'll give us our predictions. A prediction delta. These will be deltas now because there's going to be multiple of them. Is going to be the predictions minus the known result. So we now need to have a function for, let's see, what is this? An array minus this array. So array, vector subtraction. So we can actually do this right below here. This is like vector sum to like create a single one. Oh, right. This is creating a single scalar number from a sum, and this is creating a new vector. Because that's what we need to do is just subtract these. So I guess we're going to return. They need to be the same length. So okay, so the same length. We now need to return a map. So map, we're going to get the number and the index. And it's a subtraction. So it's the first one minus the second one. So number minus vector 2 index. So then this is going to be replaced with vector subtraction, our predictions, and the known results. That should be an S. Which means we also need to get the errors, don't we? Because now we're going to have multiple errors. So we need to take each of these predictions and map it into, and just like multiply them. That's I don't know if I need to create a function for it. I could just inline this. So that's going to be the prediction deltas. We're going to get our number, and what is it? Math.how. Okay, so that will give us our errors. Then we need to get our prediction derivatives. So that's multiple of these. So we're doing scalar multiply of the prediction delta. Right, so we need to multiply our each delta by each input. So I think this is actually going to be the opposite, right? We have our input, which is a scalar, and we have our errors, which is a vector. And so this will give us our prediction derivatives. I'm going to just comment out all but the prediction for right now. All right, moving down, we now need to update our weights. The weights are still an array, so this is fine. So we're going to wait through this. We're going to get the current weight, and the index, current rate, minus the prediction derivatives. So this is also a derivatives of that index, and we're going to multiply it by the alpha. So let's try this. Let's see if we can get close to it, or if my assumptions are not correct. Vectors must be the same length. So this is line 7. So our vector multiply here had input and weights. Oh, right, because this is, our input is just this. We actually need the scalar vector multiply, don't we? Prediction is not defined. Where was that? Line 43. Oh, this is predictions now. Okay, so we got through one line and then we crashed. Right here. Prediction deltas, that's why. We can see after this one go through, our predictions were 0.05. So off of this one input. And we can see it's just multiplying these. So based upon the these three weights off of this input. Oh, infinity. That's lovely. It lasted too long. I wonder if I can do it really fast. No. Okay, it went to negative infinity faster than I can like stop it right away. I wonder if I could. I kind of want to do a for loop here and just do this a couple different times. All right, so here's our 5. Here's our predictions. So 0.05. We're getting, where are we trying to go? We're trying to go 2, 1 in this first prediction from this input. So it looks like we're actually getting farther away. So I'm doing this exactly the opposite of what I'm supposed to be doing this. This second one is trying to go to 1.2. And it's also getting farther away. So exactly the opposite of where I want to go. And I'm sure the third is doing the same thing. I want to get to 0.2. Actually, this one's going down. They're going down regardless of whether or not I want them to go down. This third one actually is right to go down. It's just not going down. It is probably not going down because I want it to, but you know, just despite that. So my attempt to sort of do this on its own, I didn't do this correctly. So there's probably like a description here that I can look into, and it will. I'll probably try again off stream too to see what I did wrong, and then I'll look through its code to sort of see that. And then the next one will be the multiple input, multiple output with the matrix math for all of these. And then once once we do that, we're ready for actually using this neural network for real things, which is really exciting. Another thing I was thinking of last night was the variety of ways that a neural network like this could be used. So I was thinking of using like a game, so like an AI that plays a game. And to be really simple, I took Pong as the game, because there's only a few different types of moves that you can do. You can move your paddle up and down or just stay still. And there's lots of inputs it would have. The location of the ball, the velocity of the ball. So is it moving up? Is it moving in this direction, this direction, this direction? Like, what is it doing? And the distance of the ball to the paddle. So hello, JavaScript Gold. So if I take those, that's what, like 3 inputs? I want 3 inputs and I want 3 outputs. That's exactly what we're going to be going through with the matrix. And then I could train it by saying, well, okay, if the ball is up at the top and its velocity is up, then I want to move the paddle potentially down. Like, oh, the location of paddle, that would have to be the 4th input, where that is. So like, okay, if the paddle's up here and the ball's up here and it's heading up, move the paddle down. I can figure out all the different combinations and train the weights so that they're appropriate, and then actually make a Pong game and have it try to play it. And that would be a lot of fun, and possibly what I would do for the conference talk. What format is this? Like what format of code, or like what format of deep learning? I guess I'm not completely sure. But yeah, that's what I'm looking forward to doing, and that's next time I'm guessing we're going to get into the matrix math. So with that, let me go ahead and upload all this code. Let's see. Gradient descent learning algorithm. Currently not working as expected. Matrix math, yes. The matrix math, I think, that's the thing that that is the most scary for people, especially if they don't have like a math background. But then, like, okay, if I describe it in a non-math terms, then it becomes a lot less scary. It's not that bad, it just sounds scary. Yeah, no, it definitely does sound scary. I think the problem is that the words that we use to describe the mathematical operations are extremely scary because they're so unfamiliar. And with the number of people who drop out of math in college or high school because of bad teachers, it actually leads to people who could be excellent at programming or building neural networks like this or making games, and they just run away because they think they're terrible at math, when it's really that they just had bad teachers. All right, let's see where. So recently you've been making a JavaScript library. You call it Basic.js. Awesome. Is it like a personal library just for yourself? here is a link to the code if you want to come and check it out. You can sort of like follow along with where I've been going. All of today's stuff is the actually learning simple neural network learning. And that's because the network is now learning. It is coming up on the end time for the stream. So I am probably going to go get ready for the day. In 3.0, you'll make it open. Awesome. And I forgot what I was saying. I'm going to go get ready for the rest of my day. I hope you all have a great rest of your day. If you're enjoying what I'm doing here, then please, well, I mean, feel free to follow me here on Twitter or on YouTube, or just send me messages, just saying that you enjoyed the content. If you have feedback, I also love to know how I can improve and get better. Thank you everybody for stopping by. Let me see. I have enough of you. How do I see where? Is there anybody? Oh, really? Speakers don't do anything. Mute. Oh, is Nibbles on? I've got an advertisement, so I can't tell if he's near the end. Nibbles.io has rated us several times in the past. So if he's live and he's still on for a while, he's taking a break. All right, well, I don't have anybody else who's online. So I am going to go ahead and send you all over to Nibbles.io. He has sent some people over to me in the past. He's done, what has he been doing? He's been making a computer language. He's base code. The journey starts with one step. So I don't know what he's doing right this second since he's taking a break, but I feel confident enough that I can send you all over to him. And how do I constantly forget how to actually raid. And every time we've done it, this ended in a terrible, terrible disaster, but maybe not today. So I'll go back to my dashboard. Where's the raid button? Raid and host. Pick a channel. So I want to go to Nibbles.io and I will raid. All right, everybody. Thanks for watching. I hope that you enjoy whatever Nibbles.io is creating. Treat them well, and we'll see you next time, whenever, which should be Wednesday morning at 6:45 a.m. All right. Bye.